on. Bardiyat University is named after one of the most, if not the most influential Tamil poet, Bardiyat. And so Professor Balachandran is well known in control theory and differential equations on Banach spaces and also in the recent years control of PDEs and so forth, a wide range of areas. He has also graduated 28 PhD students and 28 PhD students, and Dr. Saktivel was somewhere here. Hello, Saktivel. So he is, for example, his former student. So and a bunch of students are here. So very it's a privilege to have Bala here. So he is going to talk about controllability of fractional dynamical systems.
So thank you very much. So first let me thank Dr. Uppal Manna for inviting me to give a talk here. So in fact, I came here because of Professor Sridharan. He only motivated me to go out of my shell. So I am always within my university. I will never move out of my cell. So he only invited me to US and exposed the area of partial differential equation where we have done some work. And before that I was always interested only in ODE and abstract differential equations, and along with that, because I grow myself, I don't have any mentor. So that is the reason why I am choosing a least area and slowly progressed. So now only you still see that even though here it is also a fractional dynamical system only for ordinary. So not partial fractional dynamical system, which is going to be an emerging and interesting area. So for which the youngsters may contribute something a little bit later. Okay, I start with my brief introduction about the finite dimensional control problems. Oh.
Left and right here.
But he has to go back to
You keep the right one, right?
This
the right. No, right. Right button.
This one.
No, below.
This
Press that.
also shouldn't point to the audience because it's laser. So, so we need to get it back to the. No, you should point. I think you should point to there and
That's right.
Oh.
So we will have a brief results for finite dimensional control system, so that everybody knows that. So if our linear system is expressed in this form, so where your the dynamical system is represented by ordinary differential equation in this way, that x dot equal to ax plus bu, where your A is an n cross n square matrices and B an n by n matrices, and your x is in the r power n and u is in r power m, and we always assume that your m is less than n. So because so the other day that Shaktil also told that, so you have to take smaller dimension for control, so that you will control the bigger dimensional space. So that is the aim of taking that m is always less than n, and the definition is this one. So if you take any two arbitrary points in the whole of space, and if you are able to produce a control such that the solution of the system satisfies these two conditions, that the x of 0 is equal to x naught is the initial condition, that is called initial state, and x of t equal to x1, which is the final state, both should be given already. So when these things are called, then it is called controllable. Sometimes some others say it is completely controllable, globally controllable. All these things depend on the points where you have taken. So if it is a smaller space, then sometimes it is called locally controllable. If it's of the whole r power n, it is called globally controllable, or some others will take completely controllable. All these things are there, and the time is also fixed. So here this result is a standard one. So the system one is controllable if and only if rank of this matrix is equal to n. So this was first proved by Kalman. So he only proposed this problem in 1959 in the IFAC conference, where this problem was introduced, and he later on studied about these things. And one Indian, that probably Professor Narendra, he has also done a lot of work on control theory. So but they stopped at certain times after the finite dimensional systems. Okay, so then you just extend it to the time varying system. Okay, so if you just consider the time varying system instead of the constant matrix A and B, if you take that time varying matrices A of t and B of t, so then you assume that it is continuous. So later part you can extend it to the nonlinear system. So here the equal condition is this controllability Gramian. Sometimes it is called Kalman Gramian also. So this is positive definite. So if the system 2 is controllable if and only if the Kalman matrix is what is that, this is positive definite. So this is also proved by Prof. Kalman. And just extending to the nonlinear system. Okay, so here if you take f, so that function f is continuous in all variable, and here that if the linear system is controllable, then the nonlinear system is also controllable provided that nonlinear time satisfies this condition. So I just take only one condition, that's all. So if you have many conditions, so that ft x comma u have properly, if you choose many conditions, so accordingly you will get different nonlinear controllability results. So for that you have to choose different fixed point theorem. So when if you take your f satisfies the Lifschitz condition, then you can apply your Banach contraction mapping principle where that solution is unique. So when you choose this kind of conditions, you always choose that either Schroeder fixed point theorem or that Krasnowski fixed point theorem, like that. So this is the one thing. So now that technique is based on Schroeder's fixed point theorem, which I will use in the later part of fractional dynamical systems, so not now, it is a conventional one. And with that, so these are all finite dimensional systems. With that, several results on controllability of integral differential system, nonlinear delay systems, and neutral integral differential systems, singular systems, and second order systems. This all already has been studied in the finite dimensional system, and you have a vast literatures on this area. And we will move on to that an infinite dimensional control system, which is always covering the partial differential equations. So here is this system. So that is x dot equal to ax plus bu, where A instead of a matrix, its A generates a continuous family of semigroup of bounded linear operators on a given Banach space x, and B is a bounded linear operator from Banach space u into x. And now the classical solution is always only in domain of A, so not in the whole of x. So therefore, as far as studying the controllability problem, so you should not take that classical solution. So if that case means you will get only the local controllability results. So therefore, so in the infinite dimensional system or that abstract differential equation, you have a nice solution that is called mild solution. So that mild solution is always an interesting one. So if you take the space, so why we want to take the mild solution is, if you take the space, this is x, so this is your the domain of A. So when your x0 and x1 are here, so if the solution is classical, so it is not controllable. So that's why that we want to take only the mild solution. Mild solution exists whenever that initial condition is in x, that whole space. So whereas whenever that initial condition is in domain of A, you will get only the classical solution. So that is not sufficient to get that complete controllability, or that's any point in the arbitrary point in anywhere in the space is not possible to control the system. So in between there is a solution called a strong solution. So that is depending on that the concept called in pure mathematics called almost everywhere. So that the differentiation is almost everywhere means that this solution is called a strong solution. So in between, so you have many generalized solutions which sometimes called viscosity solution and other solutions. It's all depending on the problem which you have to take. So with this, the solution is represented by using that semigroup of operators. So this is called variation of parameter formula for this equation 4. Why I want to stress this? So that later on this variation of parameter formula is not possible to extend it to the fractional differential equation. So that is the difficulty of fractional differential equations. So here you have this exact controllability results. So the definition is the same thing, and you need this hypothesis. So the linear operator from W2 from L2 to X induces an inverse operator. So this is the strongest condition. So that is the difficulty of establishing good results in abstract control theory. So due to this one. So for this linear system, if you just take U of t equal to this, you will get that exact controllability. Then, so there is a caution about this abstract control systems. So if you take that X is, so of course if it's X is always a infinite dimensional space, and in that case your system is never exactly controllable when your operator B is compact or the semi group is compact. So that is the difficulty of these things. So later on this was proved that there S of t is compact for t greater than 0, then later on that Lewis and Wechsler. So this result was a famous result proved by Trigioni. So even though Trigioni proved this result in 1980 and 77 like that, so even if you look into many of the literatures in abstract control theory, people are keep on using that compact operators, so which is not advisable. And then later that Lewis and Wechsler proved the same thing. So for when S of t naught instead of t, he has taken an arbitrary time t naught which is compact, and S of t is differentiable. So that semi group is differentiable and it is compact, means it is impossible to prove the exact controllability. The reason is when you take the compact operator, that okay, so this W from L2 to X, so this gives that your W is a compact operator. So when W is a compact operator, and everybody knows that the range of a compact operator is always finite dimensional, which leads to that your infinite dimensional space become a finite dimensional space, then that leads that your abstract differential equation becomes an ordinary differential equation, which is already discussed. So there is no use of extending any results by using compact operators, but that becomes just matrix equation. So that's why that this is a like no. Okay, so and then so therefore, so to overcome this difficulty, people started to introduce a new concept called approximately controllable. So this is the definition is this. So the system is said to be approximately controllable if the range of the closure of the range of this is equal to the whole space. So or if you put the definition of like this is nothing but your denseness definition, that's all. If you take any point x1 in X and an epsilon greater than 0, you can always find a control U. So such that the solution at time t and this point x1 is very near. So that is called approximately controllable. So several results are proved by using fixed point theorem and other things about approximate controllability. So in proving approximate controllability, this compact operator will not make any trouble. So that is one advantage. So that's why people are interested in approximate controllability, because several second order operators are always generates compact semi groups. So that's why that is a thing of abstract controllability. Okay. So now just you extend it to that nonlinear control system in infinite dimensional space. So you have to take that F. So where F is a nonlinear operator, so you have to take any kind of nonlinear operators and impose proper conditions on F or G or this F. So this is called integral differential equations. This is a general integral differential equations where you can have the controllability results by assuming proper conditions on this F. So then you can also extend this result to delay systems or neutral systems. So the same thing is possible by just extending these things. But here also be careful about that using that compact semi group. So that is the thing. So without compact semi group, by applying the Schadar fixed point theorem is always very difficult. So that is one thing. I just want so in this space I just want to talk about a small anecdote about occurred in my case. So when I am doing all these things, so Professor Sriran invited me to give a lecture at University of Wyoming. So there I talked these things, and he suggested that don't do all these things about abstract systems. You just straight away come to your partial differential equation and do something. So at that time the Kalman technique, the Kalman estimate technique is a very interesting one, and he has done a lot of work with professors at Romania, so, and probably Barbu and his students. So he suggested me to introduce you come to that partial differential equation areas, and he suggested that you read Kalman estimate technique. And I came back to my university and picked Shaktivel. And we both, along with Professor Sridharan and probably that Shaktivel, went to that every doors of DAFR and other places and learned that Kalman technique. So it is a wonderful experience for us to coming from ODE to PDE. So it is very difficult task. After 5 years, he was able to submit his thesis, and after that we produced 2 more results on controllability of partial differential equations by using Kalman estimate. Then after that, so there also we come across one big problem. So when that technique was extended to integral differential equations, partial integral differential equations, so we do not know that it will be automatically, we thought that it will be automatically extended, and we worked hard and get that paper published in Journal of Mathematical Analysis and Applications. After that, one gentleman from France pointed out that one inequality is wrong. So when we looked again, we found that that inequality is wrong, but we will not be able to fix that inequality even after 5 years. So then we withdraw the paper.
Even the problem itself is still open.
Still open. So that is the thing then, so that nowadays we don't find any paper on Kalman estimate. I don't know whether it is stopped. Unfortunately, I also leave from other area, that is this fractional differential equation. Probably my students, nearly 10 students are attending this course. So if they may pick something from this course, if they will be able to do something on Kalman estimate and other things about partial integral differential equation, means it is a wonderful accomplishment for this particular school. So that is my aim also. So that's why I want to take that Professor Sridharan push it to partial differential equation, and unfortunately by doing something after that I again came back to ordinary differential equation. It is my weakness, because there is no motivation in that area. So therefore I am again coming back to ordinary differential equation in a different sense, that is called fractional ordinary differential equation. That's all. Okay, so we will go to this. So it's an interesting one also. Okay, so I think that calculus was introduced by Leibniz and somebody called Newton, so we don't bother about that. When Newton, so Leibniz sent a letter to Yale Hospital. So he has asked that meaning of that derivative when n equal to half. So it is an interesting question at that time, and so he has not given any clear answer, and he says that maybe in the future some may be given answer about these things. So that last week I happened to read a book on Ramanujan. We will never thought that Ramanujan talked about fractional differential equation. So he has done something on fractional differential equation only for the function f of x equal to x. So he has not given any formula, just given a fractional differentiation for this particular function by using gamma function, then he stopped. But finally that fractional differential equation, when you go back to that, it was introduced in that 17th and 18th century. So they used only his ideas. So, but unfortunately he stopped there. I don't know about that. It was given by that famous book written by Ranganathan. So that great librarian, he has written. Because of this year we have to celebrate that Ramanujan's 125th year in our university. So we want to prepare something. So there I found that this one. It is really an interesting one. So that Ramanujan also touched every basic area of mathematics. So integration or differentiation or infinite series or all these things. So that is a wonderful observation. Okay, so this is the definition. Originally this was introduced by that Letino and Grunwald. So they introduced this one. So just by extending that our Leibniz rule to this one. So this is the definition of these things. And after that, Riemann and Liouville introduced this fractional integral operator of this form. So when f is an integrable function, so this is your integral operator.
Now, previous slide, what is alpha r? Previous slide.
Next one, the previous one?
Previous. Alpha r, what is that?
That is fraction.
Alpha by r.
But no, alpha is fraction. Oh, this is permutation combination.
But alpha, what is alpha? Alpha is supposed to be fraction.
No, he introduced this one. So it is not my definition, it is the definition of these things. So then only it was exchanged to this way. Nobody is using that definition nowadays. So only people are using this definition. Okay. So now this Riemann and Liouville introduced this definition. So this is an interesting one. So after that, okay, so this satisfies some interesting observations. So it is our conventional integration properties. So this linearity and commutativity and semi-group property and reciprocity, all these things are satisfied where this d alpha is our fractional derivative, which we are going to define in the later part. So this is the Riemann-Liouville fractional derivative. So here if you see that, so the derivative after integration, the derivative is taken. Okay, so this is the case. So when alpha is lies between, actually that people are working only on this 0 less than alpha less than 1. So people are not working on other things, and now that people started to working on 1 less than alpha less than 2. So it is an interesting case when we deal with about partial differential equations, because so in that case it covers both the heat equation and wave equation. So that is one interesting things about PDE. Okay. So when alpha goes to 1, it is heat this way. Okay. So therefore people are clubbing together, and instead of discussing different one, they discuss this one, and it is slowly picking up this kind of equations in fractional partial differential equations and other things. So here also a lot of things are there. So to find a numerical solution, other things that I will talk about in my end of my things. Okay. So now the only disadvantage about that Riemann-Liouville derivative is, even if you differentiate the constant, it is a function later on. So that is so conventionally in the integer derivative, when you differentiate a constant, it is equal to 0. So whereas in the case of Riemann-Liouville derivative, it is a function. So giving physical interpretation is very difficult. So and also that it gives that singularity when at the lower limit. So that 0 to t means in the lower limit it becomes singular, and this should be an issue when applying the boundary conditions. So especially for controllability, it is nothing but a boundary value problem. It gives a great difficulty on all these things. So and the Laplace transform of the Riemann-Liouville derivative depends on the fractional derivative at 0. So this is also an issue when solving the initial value problem. So that's why that people are not that much interested in Riemann-Liouville derivative. So to come across or to overcome this difficulty, one Italian, so probably he has done a lot of work on theory of elasticity, and he only introduced this definition for fractional derivative. So he puts that derivative inside the integral and taking the integral and all these things. So here you will get a nice result. So this definition is nowadays often using for fractional derivative, and so here you will get nice interpretation for the physical meaning and other things. So therefore people, so especially engineers, are using only that Kaputha derivative instead of taking Riemann-Liouville derivative. So that is one advantage, because here that differentiation of that constant is 0. So that's why this is an most important one. Okay, so this satisfies, or of course it is not satisfying that equality, and it is, so that is C alpha C beta is not equal to d of alpha plus beta, and it's also not commutative, and there is a relation between Riemann-Liouville derivative and Kaputha derivative. Here you have that these things. So this only gives that when you differentiate that constant, it when the Riemann-Liouville derivative, it gives a function of time. So that is one unpleasant situation. Okay, so now, so here when you are giving some physical example, so how to break that fractional differential equations. So for that there is a concept called sequential derivative, because so when you are dealing with ordinary differential equation, you see that so I just give a small example, that's all. Equal to x means if we want to write it in matrix, so if you want to write it in matrix means you can take that x equal to x1 and x1 dot equal to x2. So then your x2 dot equal to your x double dot, which is equal to x which is equal to x1. So therefore you make it as So some matrix. So for this case it is 1, 0, 1. Okay. So therefore, if you take this is equal to Z A, so then Z dot equal to A Z. Okay. So we can convert it into matrix differential equation for the ordinary differential equation by changing small change of variable, but that things directly not possible. So therefore, they introduced the sequential fractional derivative by this way of definition. So there you can have the integer. So your alpha is fraction, but your k is there. So this is very useful for converting these kind of things, so that you will get a matrix fractional differential equation. So that is the advantage. So here it is a fraction. So this notation gives that when alpha is greater than 0, fractional operator, less than 0, integral operator, 0 is identity operator. Okay. So then by using Laplace transform, okay, so these are all elementary things we need not worry about. So students can understand this. Okay. So now, so this is our fractional matrix differential equation. So A is an n by n matrix and your F is a vector. So and C is the Kappa derivative, and by using your this Laplace transform technique you can write. So these are all the technique and how to get that solution. The solution is so for writing that solution you need a special kind of function called Mittag-Leffler function. So this function is the generalization of our exponential function. So when you take alpha equal to 1 and beta equal to 1, you will get E11 z e power z. So therefore this is a generalization of the exponential function, which is very useful for writing the solution of these things. So for that Mittag-Leffler function also you can take the Laplace transform and other things, that is these things which is not necessary. Okay. So by using that Laplace transform for Mittag-Leffler function and that equations, so you will get a solution representation. So once you get a solution representation means you can always study the controllability problem and observability problem. So all kind of things. So here when you use this, you will observe that here it is E alpha. So E alpha alpha. So therefore this is not the variation of parameter formula. So that variation of parameter formula is possible in the ordinary differential equation and abstract differential equation. So whereas it is not extendable to the fractional differential equation. So that is one difficulty of not extending every results to fractional differential equations. And this satisfies this one satisfies these things. So because of this good quality only we are able to verify that this equation satisfies the given fractional differential equation. Okay, then just comparison the results about ordinary differential equation versus fractional differential equation. So that chain rule is applicable for ordinary differential equation, but not yet applicable in the fractional differential equation. And Leibniz formula available, so it's just partially available. Trichel formula available. So variation of parameter formula is available for ordinary differential equation, but it is not possible here in the fractional differential equation. Laplace transform in both cases is there. So existence uniqueness theorems, so we have rich history of ordinary differential equations, and this just developing. So that fractional differential equation is just developing about that existence theory, and that boundary value problems also like that. So ODE have many works, and FDE just few papers are appearing, and stability analysis is also rich results are there. Here fractional differential equation is extremely very limited. So I can say that just some 15 or 20 papers only available for fractional differential equation about that stability concept, and geometric and physical interpretation available for ordinary differential equation. Here it is not yet available. So that is one disadvantage for fractional differential equation for that applied side. So when there is no physical meaning means people will not be attracted. So that is one reason that so only that mathematicians are doing. So that is one thing. So stochastic analysis, so it is well developed, and I don't find anything about fractional stochastic differential equations, either ordinary or partial. I don't know about that. I don't find anything. Even I tried that getting that notational representation makes difficult for me. So that gives the trouble with the fractional Brownian motion and this fractional time derivative. So that is I stopped there. So controllability results, ODE is very rich. This is just starting. So this is in the initial stage, and applications plenty, and here also plenty. You can look into journals. You will find that half of the papers are coming nowadays in fractional differential equations. I just want to say that controllability results. Not just started. just started. I found that only that Adomian method is used only for studying the numerical solutions of fractional differential equation. I don't find any other method. So I don't know whether it is possible for other numerical technique for fractional differential equation, and especially for even for ODE itself, it is very difficult. I think so. So then thinking of PD is a little bit difficult, I think. Okay, so this is just our conventional system. We changed this derivative in the fractional one, and naturally you will get that solution representation for 7. So this is the solution representation. Once it is possible, means you can apply our conventional definition, or that controllability problem is the same thing. And here you will get the controllability grammar. Instead of this is always conventional in the ordinary differential equation. Here is the extra term. So this is the, so some others use this term in this before this control variable. So when we discussed about this with some engineers, they suggested that instead of putting here, you put there. So therefore, that now that controllability grammar for fractional differential equation is only in this form. So not without this. So for this controllability grammar, if you take that control variable, this automatically satisfies the system is controllable. Conversely, it is also possible that if this system is controllable, then the controllability grammar is also positive definite. Okay, so the system 7 is controllable if and only if the controllability grammar is positive definite. So just to extend it to that, so everything available, whatever available in the ordinary differential equation, you can extend it to the fractional differential equations by some strict conditions. That's all. So here the same nonlinear term ft x comma u, and only thing you have to assume the same. Okay, so you assume the only same condition for ft x comma u. I just make this only for making that formula to these things. So that's all. So this is the same condition. Okay, so this we have already started in that ordinary differential equation. So this condition with the condition on the linear fractional dynamical systems, the nonlinear fractional dynamical system is also controllable. Just I am always using that fixed point technique for solving nonlinear controllability problem. So only that for the partial differential equation we have used that Kalman technique for linear system. When we go to that nonlinear system, we used that multi-valued map. So there also we used only the multi-valued map, the fixed point theorem, that count fixed point theorem, other things. So now this control u of t. So if you define these things, so this control will satisfy the required boundary conditions. So now, now we are able to prove that there exists a fixed point for this integral equations. Then that fixed point is the solution of this integral equation, which in turn is the solution of the given differential equations. So that solution satisfies that boundary condition, that x of 0 is equal to x0 and x of t is equal to that final condition x1. Then the system is controllable. So therefore, that controllability problem is automatically converted into a fixed point problem. So once it is a fixed point problem, means you can choose any kind of fixed point problem according to your choice on the matrix A of t and B of t and the nonlinear function. So that is the thing. So here we have taken that one, and you can always use that Schroeder fixed point theorem and prove that nonlinear system is controllable. Okay, I just gave an example. So this is the thing. So just taking this one and introducing this control. So this is without control. So this is called a fractional harmonic oscillator, and if you introduce that control variable, so here you have 2 alpha. So this is only sequential derivative. So this we need that. So you just take that x1 of t equal to x of t and x2 of t equal to your fractional first one. So then this becomes this way, and it becomes that matrix fractional differential equation where your A is this and B is this and your x is like that, and for that you will get the Mittag-Leffler function. So that is not easy to calculate. You have to use MATLAB. So by using MATLAB you can do all these things, and finally you can say that this controllability grammar is positive determinant where your M1, M2, M3 are all big expressions. So this is the big expression. So it's not hand calculation, it is not possible. When in the case of ordinary differential equation, you can find that exponents, fundamental matrix is a little bit easy. So in the case of ordinary differential equation, when in the case of fractional differential equation, even for simple case, the solution is always a series solution. So that is one thing. So probably some special functions are always related with fractional differential equations. So in that sense, I am always thinking about that Ramanujan has made a lot of special functions. Is there any connection between his special functions and that fractional differential equation? So that is my one intuitive problem always in my mind. Okay. So this is thing. So that if you choose this UOT, then that fractional harmonic oscillator is controllable. Okay. So this is one thing. So it's just already that result is proved for that controllability of a linear dynamical system with integer derivative, and this is with prescribed controls. Here this control is prescribed. Okay. So that value is given, and this result, and you can extend it to the nonlinear result also. So this also can be extended with a lot of conditions on that. So this is one interesting result. So there is no condition on the controllability. So it is so no constraint on the control variable. When you make that constraint on the control variable, we can also possible to study the controllability problem. So this paper was published in that IET Journal of Control and Engineering Journal in published from UK. So it is just accepted, this paper. So this you have that lot of machinery to these things, so just defining all these things and try to prove this. This is our Kalman matrix in the fractional setting. So this you have to say that it is positive determinist when you can say that it is controllable with constrained control on the control variable. So it's a nice problem, but in this area only very few papers are appeared. So that is one interesting things. And just I have this proof all other things. So it's not it's not necessary for this. Just to know these things. And here you can write the solution, and here you have this nicety of that control variable in a nice manner. So therefore you can get that boundary condition is automatically satisfied, and the proof is by applying again the fixed point theorem. So usually I am using that Scholar fixed point theorem, where you can get that nice result. So this is one thing, and this is the continuation of these results. And I am also here I have given an example. Or it's a nice electrical circuit model. So this is the model where you can get system framework of this form. So this is the case that equation 24 is of the form where your fractional derivative occurs, and this is the setting. And finally this becomes a matrix fractional differential equation. So the 27 is this form, and this can be written this way. So this is just our these things. So therefore, so by using some conditions on the constants, so this has some physical meaning. So by using that conditions, we can always so say that this system is controllable with constrained condition on this control variable. So this is one interesting applications for from electrical engineering. So because of this application only they accepted that paper. Otherwise they rejected that. So you give one nice example from electrical engineering. Otherwise, so because this is an electrical engineering journal, so they insisted a good application. So we searched that and we tried to. This one. That model is already there in that one. So this one, it is in 14.
Voltage is equal.
It is in 14. So shall I show that reference? Yeah.
What's 14?
Oh, I will show that. A reference, yeah. This here. So they gave only that without control variable. So I took that and applied that control variable and select that constraints. So it is very difficult to fix the constraints. So it will not satisfy for all the constraints. So therefore I chose that u of 0 is equal to 0 and u of t equal to 2. So maybe for other things we have to search. So it is just trial and error.
Voltage and current are related by this alpha roles, and some kind of saturation is there due to the medium or something like that, right? Something like that. Yeah.
So that is it. Oh, that's this all other things that what is the controllability Gramian and other things we have found that so this moves that from 0, this 0 means 0 0 0 to 1 1 1. So this is possible by this control. So that example is possible these things, and you can keep on changing that. I think we can get even finer results also. You just want, because we have the mathematical theory, we want to fit it to the physical example. So that is our aim, and we fit it. Maybe in future we can get finer examples also. So that is possible. So this is as far as fractional dynamical system in ordinary differential equation sense it is there, and people are working on partial fractional differential equations, but nobody is working on controllability of partial fractional differential equations. And very recently I saw that one paper published by Professor Yamamoto. So he establishes that this one. So this he has established Kalman estimate. So when a Kalman estimate technique is possible for fractional partial differential equation, means naturally we can expect that controllability of that fractional partial differential equation. So it represents a heat equation. So he called this at fractional heat equations. So he established, just it appeared only in 2012. So it is a very recent work. Only I think of late only that Professor Yamamoto is working on Kalman estimate. So nobody is working on this area. I don't know about that. So maybe with this we want to extend this result to partial differential equations with our group research group. So that may be our future research area about that. So thank you very much.
I guess it's a very simple question. So, as regards boundary value problems for fractional systems, I wonder how to determine the number of required boundary conditions in function of the degree of the system.
Yeah, I think it's sort of he's asking how do you know how many boundary conditions to put, or even how many
that I don't know about that.
or even
I just know only
initial
things about fractional
what's the
differential.
Cauchy-Kowalski theorem, right?
That I don't know about.
Right. How many initial maybe, right? So maybe the fractional derivative and the
No, in your system, alpha less than 1, right?
Yeah.
You gave one example, right?
Yes, alpha less.
Alpha less than
Yes,
1.
yes.
And the initial condition?
Which one?
In your initial condition?
no, this should have been 1 and 2, right?
No, that is general case.
No, here.
No, he is asking about.
To your system. Electrical engineering. Let us see your system.
Initial condition is 0 0 0. See this one.
Example.
Example. Right?
0 0.
So that means only one initial condition.
Yeah, only.
That's what.
But if it is 1 and 2, then you need to go from initial data, one initial data to 2.
That case is a peculiar case, you know that so people are.
Yeah, so that's what you meant.
No, this is the general. This case is now people are attacking this problem. So because it covers both the heat and wave equations.
Yeah,
So that's why they are all.
example maybe his comment applies because
But I am not familiar with this one.
yeah, what happens is for heat equation you just put one initial data. Wave you have initial data as well as the speed, and so maybe fraction. Maybe you put the fraction.
Answer? You have to find you take
Answer to the question I just posed.
No, to my question.
Boundary condition, boundary value problem, or initial.
For instance, initial.
Let's say that the alpha, the differential.
He's talking about 2-point boundary problem.
Yeah.
Fractional derivative.
So the same. That is the definition of controllability.
Problems, right?
Yeah, he asked how you.
It's just a 2-point boundary value problem.
You want to talk about
Boundary
fractional.
Initial condition.
No.
Then this is
Only the time derivative, not space.
Saktivet, let the speaker.
Yes.
Yeah.
No, I don't know. I am talking only about the fractional derivative of OD. I don't know about that one. Okay, I don't know. At present, I don't know about that. No,
I
no.
think it's
No, I am not more or not much meaning about that fractional differentiation. I just started now only, just for 2 years back, so because I don't know about that physical meaning and other things about fractional differentiation.
question. Any other? Yeah, Professor.
Just wanted to make a comment that related stochastic problems, I think
Stochastic?
other equations have actually been studied. So it is worth investigating closer relationship between what you've been talking and those papers. I can give some references later.
This is question.
Oh, you said it's been studied, so. Yeah. Professor Booker, you had a question?
Suppose I have a function. Suppose
Louder.
the second derivative does not exist. So if I take the 1.99 or 1.999 fractional derivative,
Which one?
no, I'm asking, I have a function and second derivative does not exist. So if I'm asking that if I take the 1.99 fractional derivative, will it be fine?
Yeah, in certain sense, people will take only that up to 1.5, 1.7 like that. They don't take that 1.99 like that. So that kind of things I don't know
So
about that.
he defined the fractional power by a singular integral, right? So as long as that integral is well defined, that particular fraction is defined. So I also wanted to, yeah, Professor.
Look at the minus d square by dx square. This is a positive definite operator. Now this one you can take the fractions. What is the relation between this and this one?
Which one, sir?
Take minus d square by dt square.
Okay.
Okay, this is a positive operator. In some space, d square, no, not x. Minus something. You call that the operator A. Okay, this is a positive definite operator in some space. Now we take this fraction of that. What is the relation between that one, say, to the power of half or to the power of 1/4? What is the relation between this and your fractional derivative?
I think
I don't know.
my hunch.
I am not that much expert on that field.
Calderon and
That is a different one.
yeah.
He uses this one. Minus
Yeah,
Laplace
so
equal power
there's a
of
connection between through Calderon Liechtenstein work and the pseudo differential operator. So you have a connection between singular integrals, a way of defining fractional operators, and pseudo differential operators. So that's the question I think you're asking, right?
Yes.
If he defined
Exactly.
singular
So
integrals.
way of unit transform, you can do that.
Yeah.
Here he is using via the Laplace transform.
Yeah. So it's sort of like a singular integral because he had a factor, right? So there's some interesting connection to be explored, I think, through connecting to harmonic analysis approaches to PDEs.
Because the recently a lot of work is going on with fractional Laplace, right? Caprelli and others. Is they really is they anyway connected with this because they convert this into standard heat equation in the across space and then possible limit in the Neumann boundary that necessarily gives the fractional Laplace. So is there a way to do that?
This is fractional Laplacian that you are talking about.
Yeah.
His operator is the adjoint of fractional integration through this gamma function and so on. So there is a differentiation and integration in the fractional sense. When you
We have the difference because if you take the problem now, you can identify the fractional Laplacian. Here it is also doing the same thing. If you took a t1 minus t to the power of 1 minus alpha minus 1, corresponds to the sum of exponential denominator. So there must be some relation between these two. Is what I mean.
Any other question? So certainly in the coming years there will be interesting debates and connections between this subject, pseudo differential operators, singular differential, singular integrals, and so forth. So thank you for a stimulating talk. But we do take a 5-minute break.
10 minutes break. Technical break.
So 10 minutes break. 10 or 5? Organize, you guys are the boss.
10 minutes break.
10 minutes break. Good.